Let's define an inverse function. First, suppose we're given a function f that's one-to-one and has a domain A and a range B. The inverse of f is denoted f raised to the negative 1, and we define it to be the following, which states f inverse of y is equal to x if and only if f of x is equal to y. And where we're given that the domain of f inverse is B and the range of f inverse is A. Now, let's go ahead and do a computation. This is example 1. Given f of x is equal to x squared, and that f inverse of x is equal to 16, let me denote this x as x bar. Find the value x bar. First, let's write our inverse. F inverse of x bar is equal to 16. By definition, this is then equal to x bar f of 16. We're given that f of x is equal to x squared. Then plug 16 into x squared. The answer to this question then is x bar is equal to 16 squared, which is equivalent to 256. Now, before we move on to the next property, I want to go ahead and make a comment on example number 1. In example 1, we were given a function f of x is equal to x squared. This function is not one-to-one, so this means that our inverse function isn't guaranteed to exist. But what we can do is we can always restrict our domain for functions like f of x is equal to x squared, so that the function on that restricted domain is one-to-one, and there we can define an inverse. In this example, we just assumed that we were looking at a restricted function, and so our inverse was well defined. We'll talk more about this subtle point when we look at how to find inverse functions. Now, inverse functions have a very nice property. We saw this in the very first example, that if you apply an inverse to the function, you're going to get back what you started with. Let's write this idea down formally, and we're going to go ahead and call this the inverse function property. Let f and g be functions, then the following two conditions occur. 1, f composed with f inverse is equal to x for all x in B. And number 2, f inverse composed with f is equal to x for all x in A. This is always true for any f in its inverse. And we can make a further statement that inverse functions are in fact unique. Further, if g satisfies 1 and 2, then g is equal to the inverse of f. Let's go ahead and apply this to an example to determine if two functions are in fact inverses of each other. Example 2. Given f of x and g of x, determine if they're inverses of each other. We'll need to use the last property of the inverse function properties, which states again that if 1 and 2 apply to our function g, then g is equal to f inverse. Let's go ahead then and compute f composed with g and g composed with f. This is then equal to the cubed root of x plus 4 raised to the third power minus 4. The cube root raised to the third cancels each other out, and we're left with this as being equal to x plus 4 minus 4. And this is equal to x. So far, we're looking good. Let's go ahead and compute number 2. G composed with f of x. This is going to be equal to, Oops, I forgot to record that. So let me go ahead and just walk us through this step here. So this is our first function where we plug in f of x for each x in g of x. Then we notice that we have a -4 here and a +4 here, which cancels each other out, and it leads to this equation here. X cubed raised to the third power cancels each other out, and we're just left with x. Since g and f satisfies properties 1 and 2, that means that g is equal to f inverse. Let's see one more computation involving the inverse before we move on to the next section. This is example 3. And first, let's go ahead and assume that the function we're working with, f, is going to be 1 to 1. If f evaluated at 3 is equal to 2, then find f inverse evaluated at 2. Since we're given f of 3 is equal to 2, by the definition of an inverse function, this occurs exactly when we have that f inverse of 2 is equal to 3. And here's our solution.